Okay, I'm live. How's everybody doing? People are still here. That's good. How's assignment 1 going? Pretty good? There's been a lot of conceptual questions in office hours, which I actually think is correct. I would think about it this way. I've given you kind of 4 concepts, like this idea of multi-core, SIMD, multi-threading, and a little bit of superscalar. I think that's all. Yeah, 4. And so step 1 is for you to understand them kind of all in isolation, completely in isolation. And your written assignment that is out, you can start taking a look at, definitely, you should be able to answer those questions, right? Like that's like concept from the slide, apply it. I bet you can answer those questions. When we go to the programming assignment, you're now running on real hardware. And real hardware is a little messier. And that real hardware is basically composing all 4 of those concepts together at once. And so it's okay if you're like, well, based on first principles, what we said in lecture, I should observe this. But I'm actually observing this, and so I'm a little bit doubting my understanding of the core principles. Just come into office hours, we'll talk about it. Often I can say, no, your understanding is completely correct. It's just some effects are mixing. You know, the 2 things you understand are now mixing and interacting. And you can explain what you're seeing, you just have to think about it a little bit harder. So the mixing of it, I think, is where it gets a little bit complex. And you're just going to see it over and over again, and you're going to become much more acquainted with it as time goes on. So I would not worry too much. I'll put it this way. 1 year in this class, a long time ago, we had final projects where people could like do anything that you wanted. And probably the most creative project that I've ever seen is like, a student came up to me and says, everybody works so hard in this class, but when you kind of think about it, like everything you teach us is stuff that people do already. You get busy, you go do something else. Or, you have 10 tasks to do and 3 people to do it. You kind of just go, you do that, you do that, you do that. So their final project was to actually ask a bunch of exam questions or midterm questions to people on the street, like in a TV show. Except they answered the questions, they asked the questions in terms of like real life metaphors, and actually wanted to compute like what the average person in the world would get on a 149 exam if they just didn't have computer science concepts in it. And they actually scored pretty good, so I thought it was a pretty good final project. So, the stuff is actually conceptually challenging because of the composition, but it's actually quite easy in first principles. So you'll get it. But one thing I wanted to do is I want to go over a lot from last time again, given what everybody's asking me. And let's talk about a lot of this as a class. Because last time was the first time I was kind of forcing you to think about what does the parallel program mean in terms of what should it compute? And then there's a whole bunch of questions about how does it actually run on a computer? And to keep those very separate in your mind is a very, very helpful skill, both as a programmer or if you're ever designing any system. So here is just the same example from last time. I'll page it back in for you if you forgot. This is the same example even from last week, which is we have an array of numbers, and we're computing for every element in that array, we're computing the sign. And this is just normal C code. And at some point, I call this Ispc function. And an Ispc function differs from a normal C function in what way? Like when I call a normal C function, it's like go look up, if I go to the code, I go to this code. If this is the normal C function, my control just transfers to the top of this function, and I run those instructions. I do what the program says sequentially. And then I end up going back to the caller, right? So how does an Ispc function differ from that? Yes, sir?
It's like 8 instances of the same thing with the local variables.
Exactly. So this function call here is not saying just move over to that sequence of logic and run it, and then come back. It's saying, I want you to move over to this sequence of logic and run it gang-sized times. And let's just say our gang size is 8, because that's what's true in my illustrations. We're going to run this code 8 different times. And each time, one little detail will be different. what is that detail? The value of program index, which just says basically which time is this, which of these eight copies of the program I'm going to run, which one is this? Okay. Notice that so far I've said nothing about parallelism or implementation, but everything I've said is true. And if you want those 8 different copies of this program to together do all the work we need to do, notice that every program is sequential. This is just a set of instructions that run back to back to back. And every program does something a little bit different because its logic is dependent on the value of program index. Does that make sense? Okay. So this is the point where sort of 8 copies of the function get created, and the return value is the point when those copies have completed. Again, no talk of implementation at this time. Okay. So are there any questions about that? It's a good time to ask a question. Yes, sir.
How is the gang size determined?
It is determined, you just said it. Like at compile time in your flags, actually it's like at compile time gang size will be 8, or gang size will be 4 or 16. Yes.
Gang size is the same as how wide the ABX vector instruction is.
I wouldn't call it a coincidence, but I would say that first of all, is everything fine? Like, could you imagine a valid implementation if I set the gang size to 100? Sure. I mean, I guess my program may not handle multiples of that, but let's say if I set the gang size to 64, this program is still valid. Right? It just 64 copies of the program are going to get created, get executed, and they're all going to do their piece as defined by my code. Yes?
Does the entire gang run at the same time?
You're asking about implementation details. I'm just telling you what needs to happen. I'm telling you if the gang size is 64 copies of this function need to get run, and program index will have a different value in each of those. And so if I ran them back to back to back serially, I'd get the right answer here. Now, I'm going to put an asterisk by that in that there's a few tiny little things if you read like page 42 of the manual that actually prevent Ispc from running them serially, but that's not here today. Okay, so everybody's good on that. Okay, so it would be perfectly fine for all practical purposes if the implementation of this call was to take this function and literally throw a for loop around it, which was for I equals 0 to program count, set the value of program count, set the value of program index, and then just run this Ispc sinx function call over and over and over again. Perfectly valid, correct implementation. Now, Ispc is not going to do that. Its implementation is not going to do that, because you wouldn't use Ispc if that's the implementation you were going to get. Okay. All right. So, and then we talked a little bit about like what you should think about this program is doing is you should ask the question, what program instance does what work? And so the code that I showed you, program instance 0, just because of that for loop, if you go look at that for loop, for I equals 0 to program count, compute an index which is I, 0, plus my program index, and then increment I by program count every time, you're going to end up with a program that has divvied up work like this. Now we're going to get to implementation. The implementation is not going to be run the sinx function program count times back to back to back. The implementation, what the Ispc compiler is doing for you under the hood without you thinking about it, is doing exactly the program transformation that you implemented in part 2 of your assignment. Right? You got a straight line set of C code, and it said, rewrite that C code in instructions, in vector instructions, so that vector size things were all doing a piece of that loop at the same time. So the underlying implementation of this program, of that sinx program, is going to be as a set of vector instructions. Now the reason why you're going to set that gang size to the SIMD width of the machine is that if I'm going to do 8 copies of this program, I might as well run all 8 at the same time in different lanes of a vector. So the result of compiling an Ispc program where your gang size is your SIMD width is just a sequence of SIMD instructions that carry out that logic for all 8 instances of the program altogether. So they are run simultaneously, and they're run simultaneously all within a thread with just issuing vector instructions. So if you actually traced your program execution, you would see a thread running with scalar instructions. You'd see a normal function call, and then you just see that same thread running with vector instructions. And when it returned from sin x, Ispc sin x, it just goes back to running its scalar instructions again. Right? So once this Ispc code is compiled, it's just like normal call return of a single thread, just your Ispc code is now vectorized. Now I talked a little bit last time on I could change the program. This is me as the user. This has nothing to do with like Ispc compiler. I said I want a different program now, and I just decided instead to have a different mapping of program instances to who does what. It's a different program. It does the same thing, or it computes the same answer, but the assignment is different. But that was my choice as a programmer. And the way I want you to think about how Ispc works is a table like this. So this is iterations of the I loop. Remember, this is I equals 0 to program count by program. So 0 to n by program count. And let's say we have a gang size of 8. Now, if you go back to that code here, every program instance in every iteration of this loop over, for I equals 0 will compute some index. And so drawing out this table can be very, very helpful. Let's go right here. During the I equals 0 iteration of the loop, every program instance is a column, and these are the indices that are those are the values of the variable index in each of those program instances. And in the next iteration of the loop, these are the values, and so on and so on. Okay? Because of that code in the bottom, the code I have in the bottom right. So that was my first program. This was my second program. And it's just a different program. So in every iteration in time, the program instances are accessing different indices of the array. By the way, do you have a sense of which one is more efficient? Yeah.
Probably the one where it goes one by one, because earlier you said that when we're taking something into the cache, we do continuous.
And what do you mean by goes one by one? Because in my second program that I'm showing you here, every program instance goes one by one in time. In my first program, at any one time, at any one moment, the different program instances were accessing one by one data. Any idea which one's preferred? You like this one, because you're saying at one moment in time, I'm going to ask memory for all these consecutive indices, which happens to fall right on a cache line, and that will be much more efficient. Absolutely, absolutely. This second program creates a situation where, one instruction, like we're having a vector load instruction, and every address in every lane is separated by a whole bunch. Could actually, if this program count was large enough, every single lane would need a different cache line. So that vector load might actually need 8 different cache lines. And by the way, if they're spaced out by even more, some of them could even be paged out. So it actually could cause 8 different TLB misses, 8 different page faults. It could be quite expensive. Yeah.
So if you have your program count as a scalar multiple of the vector width, would the implementation of Ispc, would it compute that all serially, or would it actually spawn multiple threads using...
Ispc will never spawn any threads for any of the code that I've had. So what's your question? And I think it's important. So here's the blocked version.
If you had, you have a vector width of 8.
Let me go back to the interleave version for you. That's probably clear. Yeah. Okay.
You set your gang count to 16.
Uh-huh.
Is it going to serially execute the first portion and then the second portion?
Good question. So if my width of everything was 16 here,
Yes.
and I only have 8 wide vector instructions, you're asking how does the compiler implement that large gang size? It's going to issue 2 instructions. Yeah. It's going to back to back. And there's a reason why on your computers, if you modify the gang size on the compiler to 16 from 8, you will get better performance. And the reason why you'll get better performance is that think about like the vector operation here, followed by the next vector operation to do 16 wide. Those are 2 independent instructions. So you just created an instruction stream that has a lot more ILP in it, and so it's going to schedule much better on the pipeline. Absolutely. Okay. Now there's been a lot of questions about what does this foreach mean. And this foreach thing, I admit, is weird and ugly, and you're not going to see it in anything else we have in the class. But the foreach thing is the following. It's a construct that you should think of as a per gang concept. Foreach says, I know this program is being run by a gang of program instances. So what foreach says is, altogether, all of the program instances need to run n iterations. We have to run n iterations of the loop. And in each iteration of the loop, like, I is going to take on a different value. So it's kind of like saying, look, there's n iterations we got to run. Ispc compiler, you figure out how to map those iterations onto the 8 program instances that we have. I'm not going to tell you as a programmer. I'm not going to think about interleaved or blocked. I'm just going to tell you, here's the work. Please do it. Okay? So you don't know which program instance is being run, running each iteration. So another way to say that is, if I was the Ispc compiler and I saw this, I could easily transform the program into any of these 4 implementations, and it would be valid. So I could transform it into an implementation where out of the 8 program instances, the first program instance said, okay, I'll do all the iterations, and none of the other program instances did anything. I could easily transform it into my first program, where I interleave those iterations over the program instances. Or I could transform it into the blocked version. I could even transform it into a version where the program instances were like, I'll just take the next one, the next iteration that nobody else has gotten. All of those are potentially valid implementations. Now, in practice, it's going to do something like this for the reasons that were stated earlier, that it's going to get really good memory utilization. Okay? That is something I need you to understand. Is that when you see a program construct which says, here's some independent work, system, you map it to workers however you want. You don't know what worker is doing what piece of work, and you actually don't even care. You say, system, just assign all the work so I get good parallelism. I'll leave it to you to make a good decision. Because in my first program, I chose to do it this way myself. Maybe that was a bad idea on some future system, and if we would have written it with high-level foreach, some future Ispc compiler might do a better job. Yeah?
Is there any cost to making like the system decide how to extract this way?
Yes, there is. I mean, the system is going to have some policy for doing it. And maybe it's not as good as me, right? Like maybe I know my program really well, and I'm like, I want it to run this way. And so notice what Ispc has done. This is actually usually a clever design of a programming system. They give you low-level mechanisms to specify exactly what you want. And they give you a higher-level mechanism that has an obvious translation into the lower-level thing. So you're saying, look, use the higher-level one whenever you can, because it's probably going to do a good job most of the time. And if you're ever unsatisfied, you have the ability to dig deeper and do it yourself. And those layers of the onion are very, very important, I think, in good programming system design, especially in good system programming design. So let's double down here. Now this is, so here's a basic for each loop. I took all the complexity out of it. It's just for n iterations, do something. Okay, so I just abstracted it because I don't want you to think about assign x. Okay, so in most cases, if you see something like this, you actually stop thinking about program instances at all. You actually just go, I have n things I need to do, n loop iterations. Ispc, like, please make sure it's implemented in good SIMD. That's basically how you should start thinking anymore. Like, you're not thinking about program instances or gangs or anything. You're just saying, you're actually saying, oh, this for each, that's going to be, like, that's potentially parallel work. Ispc, spread them out, SIMDize it, do whatever you want. I trust you, you're going to do the right job. You do way better than me implementing intrinsics myself. Okay? But it's important to understand how it runs. Like, what does this program do? Here's another Ispc program. For every input element of the array x, what happens? It's a big hint in the function name. It's valid. But what does it do? Takes every element, computes the absolute value, and stores it twice in the output. It's a valid program. The input array is of size n. The output array better be of size 2n. Right? Okay, so that's all it does. Makes sense. And again, like if you saw this code, you wouldn't think about it as what does every program instance do. You would think about it as I need to process n elements, and for every element I'm going to take the absolute value and I'm going to shove it into these two spots, and this can be done in any order that Ispc wants. We already know how it's going to do it. It's going to interleave things amongst the program instances, but I don't really think about systems programming when I'm using foreach anymore. But here's an interesting question. What does this program do? This is a little bit more interesting. So as long as you're not the first element of the array, if you're less than 0, what happens? I slide it back. Is this a valid program? People are shaking their head no. This is important. Why is this not a valid program? Yeah. So what we've told the system, like I know what this program would do if it was run serially. If it was run serially, I'd put something in I might put something in I-1. The next iteration, I might overwrite it, or I might not. But it's very well defined what the answer is. If these iterations are run in some order that you don't know, because you've left this up to the Ispc compiler, you've said that these are independent iterations, execute them across the program instances in whatever order you wish, you have no idea what the output of this program is, because the output of this program will depend on the order that Ispc will run these things in. So this is a program with undefined output. The next rev of the Ispc compiler might come out, and your program might be a different answer, and they're well within their rights to do that, because the contract for foreach was, I'm saying that these iterations can be scheduled onto the program instances in whatever order the system wants.
Something like this?
The current Ispc compiler will make no effort to try and catch something like this. And it can't catch something like this because what if I changed x sub I into x sub a sub I for some arbitrary data-dependent a in the index? Yeah. So sure, maybe some compiler out there, if they cared, could catch this one, but I could continue to write any program that doesn't.
Is that similar to race conditions?
That's a race condition, absolutely. Unclear what the output of this program is. Okay, so here's one more that should really get you to understand things. This is a broken program for how to compute the sum of all elements in the array. Can you see why it is broken? For every element in the array, independently, please add into the variable sum, which is a per program instance variable, and then return sum. So first of all, this is actually not going to compile. Can you tell me why it will not compile? Yeah. If I'm running 8 program instances and they all return sum, that doesn't make any sense because the caller is expecting one return value. So the only way to return something actually in Ispc is if it's a uniform value, which means there's one copy for the entire program instance. So this actually won't type check. But here's another version of it where, also there's actually another conceptual problem here. I have 8 copies of sum. What will they be at the end of every program instance's completion? Yeah.
It'll just be that index that the program instance looked at.
Yeah, there'll be the sum of all of the iteration, the values from all the iterations that whatever got assigned to the different program instances. Okay? Now here's a version where I changed the program and I made sum uniform. So I could return sum if I wanted to, but there's a problem with this program. Yeah. Now we got another race condition, which is I have a single sum, and I'm trying to have a bunch of program instances plus equals into that sum. And so now I have something even, I have another race condition. Okay, and I'll talk. So here's actually how to write this thing. Oops, sorry. Did I get this correctly? Yeah. This is actually how you write this thing. So notice that I have a variable partial that's per program instance. I say for all iterations of the loop, I don't care who you allocate the iterations to, but everybody is going to accumulate their local partial. And then at the end, I'm using a special cross-instance library function that Ispc provides to perform a safe summation of this value, which is unique per program instance, to put the results in a uniform value which can then be returned. Okay. Yeah.
Does Ispc have the ability for you to write a custom lambda that reduce?
No, not right. No, it doesn't. It doesn't. But it would be conceptually easy to do. Yeah, like you could see. Trust me, this is a cross-lane operator. Yes, but so another way to check your understanding is that Ispc will compile this code. Like now we're talking about implementation of the current Ispc compiler to kind of a program 2 solution that looks like this. Notice what's going on here. For I equals 0 to n by 8, just do a vector load and a vector add. Add. At the end of this loop, I have a single SIMD vector, and every lane is a partial sum of all of the elements in the array. Can you see how that's going on? And then at the end, I need to do something to add up all the elements in the array. So I iterate sequentially over all the elements of the array, summing over that final vector. So this is a naive implementation of reduce add. Yeah.
You need to declare float at the beginning, or you can also declare uniform float sum at the beginning, or you can also do that.
No, the variable can be declared anywhere. Yeah. I was just adopting good programming conventions. Okay, so Ispc has all of these interesting cross-program instance operators that you can use if you want to think about programming in terms of a bunch of program instances and what are they doing at the same time. Okay. And so that's what I wanted to get across here. Like first, you always start by saying, what does the programming language mean and do? And then you start talking about how is it implemented. And nothing I have said here today will ever run on more than one core or one thread of one core. We have not talked about how to create more threads or anything like that. Okay? So that's the programming model of Ispc. Now, everything that we've said, you can now just replicate out, and that's the idea of tasks. So when you create a task, that's like saying, here is some work to do, and I want one gang of program instances to do it. So I can create 100,000 tasks if I want. In the same way that foreach said, here's a gazillion loop iterations, Ispc, you figure out how to assign it to program instances. Tasks are like saying, here's a gazillion gangs of work to do. You figure out how to assign it to the threads in the machine and do it however you want. So if I create 1 million tasks and I'm running on a myth machine with 8 hyperthreads, Ispc under the hood is just going to create 8 hyperthreads and then go, okay, you do the next task, you do the next task, you do the next task, and so on and so on. Okay. Now, one thing that I'd like you to mull over a little bit is if we're not using any of these cross-lane operators or anything like that, if we don't have to have these program instances communicate at all, which most of the time we don't, and if you're using foreach, I don't even ever think about program instances. I don't think about program count at all. I just say, here are my loop iterations. Ispc, you go do it in parallel however you want. Okay? But Ispc has all these concepts in it, so we can do like really advanced shifting and other stuff. Like here's an example of an Ispc program that actually computes the dot product, I think, of it computes the product of all the elements in an array. So given all elements of an array, compute their product. So one output. Okay. So if Ispc wasn't trying to be so low level, it would just probably give you a for each and say you're not allowed to have program count at all, or program instance. You would just write code, you'd almost never think about parallelism, and you'd be like, wow, my program runs 8 times faster than it did before. This is awesome. Right? So if I take out all the low-level stuff from Ispc, it turns out to be a very, very simple thing. Now, there's going to be an alternative that some of you might be, if you're a functional programming person or a NumPy programming person, you might be more accustomed to not thinking about array indices, but thinking about operations on vectors, like adding to tensors, or giving a lambda and mapping a lambda onto a collection. So you can kind of think about this Ispc program as the collection is the set of values that are referenced by x of I. So a higher level programming language just wouldn't allow you to do any indexing at all. It would just say, the data access of add is well defined. X plus y is just every element matches up with everything else. Okay? So higher level programming languages would exist and would be able to generate really fast code as well. And we're going to talk about them as well. But now you can think about if you had that in PyTorch or NumPy, how would you actually implement it well on a SIMD machine? And you have some of the tools to think about how you'd actually implement PyTorch. Okay? All right, any questions on that? Before we actually get to the basics. Yeah.
Can you go with the task thing again? Like, where did you exactly define that this is going to be a task?
That's in the program. I would like everybody to kind of, as it says in the handout, go read the manual. Or my office hours are at 1 o'clock today, so I'll take that.
So to just confirm, tasks are not same as threads, right? Like,
no. An Ispc task is just a task. A thread would be an implementation detail. But it's very true that if you create 8 tasks, a smart thing for Ispc to do would be under the hood spawn 8 threads and run them all on different threads. But if you create 100,000 tasks, it'd probably be pretty dumb for Ispc to create 100,000 threads. And I'll show you why in a second.
and a quick follow-up. If it's not Ispc and we generally write like thread code and you make suppose 10 threads, then how does it run on an 8-thread machine?
So the question was, let's say I'm back in C land, and I create 10 C++ threads, right? If I go to my activity monitor right now in my computer, there's a lot of threads. And I have 8 execution contexts. So your question is, in general, how does a computer that needs to run, apparently 700 kernel threads right now, how does it run 700 kernel threads on my computer? Yeah. It's got a context switch. So from the operating system from time to time is saying, here are those 8 threads that need to run. I'm going to put them on the processor and let the processor run. And periodically, some timer expires and the operating system says, well, we have 700 threads. We need to have another 8 run. So we're going to rip those threads off the processor and put those on. And you can imagine that could be pretty slow. So in fact, let me go ahead and since you asked, let me one second. I have a demo of that. Okay. So here's a program that I wrote. One second. Okay, so here's a C program. And it has 3 tests in it. So there's this function called do work, which literally does nothing. So the cost of doing work is just calling the function. And I put some stuff up here which says, hey, don't do anything fancy. I know there's nothing in it. Don't inline it. Don't try and optimize or anything like that. So I've got a function. Imagine that this is my task. It does nothing. So it's like the cheapest task in the world. And then here's a test which says run test 0. So test 0 sequentially calls that function. Okay? Test 1, well, actually, let me go to test 2 first. Test 2 says, right here, I'm going to create num worker threads. So I've hard-coded that to 8 on my computer. So I'm going to create 8 worker threads. They're all going to run worker 2, where worker 2 is given the total number of tasks, take the next available task, call do work, run it, and then keep account of how many tasks this thread has performed. And if we ever get to a total task count that equals n, we quit. So I create 8 workers, and they just go next, 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 next. And then strategy 1, test 1, is just for every task, create a thread, run the task, and then reap the thread, join the thread. Okay? So which one do you think is going to be the fastest? Votes? Yeah.
The task one, because you don't need the context switch and you execute them completely.
Okay, so 0, let's say 0 was do everything sequentially. 1 was spawn up an actual thread, a C++ thread for every task. And 2 was spawn 8 threads and just have those 8 threads cooperate, right? So you like 2. Okay, any other votes? 0? Any other votes? One with 8 threads, the same vote here. So let's actually run this thing. What is my program called? Oh, thread launch. Okay, here we go. So 0 finished in 1.6 milliseconds. I think I'm running like a billion iterations or something like that. This is the spawning threads. And then it just flashed test 2. So basically the sequential one, because there's just no work involved, it was just a lot easier just to call the function and take like the 8 operations to push something out of the stack and pop it up. So the test 0 was 23 times faster than test 2, which was my thread pool. And my thread pool was 300 times faster than spawning a thread per task. So this is an extreme case, right, where the task is so tiny that any overhead that you see it. But that's a 300x difference between creating a thread per task and letting the operating system sort it all out. And me just creating exactly the number of threads that my machine can use, and me handling the work dispatch with an efficient get next task kind of thing. So what do you think Ispc is doing under the hood when you create tasks? It's creating a pool of the right size and saying, oh, I'm going to divvy up. Yeah.
Now, if the function was very long, would it be still better to have...
If this function was very, very long, I would expect to see my parallel thread pool definitely outperform sequential, because I'm doing all the work in parallel.
Is it still better than... a thread is still better than one thread per task?
Well, at some point, if the function got so long, it doesn't matter anymore, because the overhead of creating that thread is insignificant. So what we could do is we could put a for loop inside my little task and make it do more and more work, and you could go figure out what the cutoff point would be. Yep, exactly. There's also a cutoff point where if it's so small, you might as well not even do it in parallel, as we saw there. Uh-huh.
When the OS is switching context, the context is taking off the processor that's just being stored in memory.
Yeah. So don't confuse context switching that you'd hear about in an OS class, which is what we are now talking about, with hardware multi-threading that we've talked about in this course. In this class, we will almost never think about operating system context switching, because we think about like we're the only application on the computer most of the time, and it makes no sense for an application to create more threads than execution context, because all you're forcing to happen is the operating system starts swapping them on and off. Your job is to create one thread per, as much work as you can do, and then it's your responsibility to take work and assign them to your working threads. Absolutely. An operating system context switch is hundreds of thousands of cycles. A hardware execution context switch is one cycle, right? Very different. If you use operating system context switching to hide the latency of a memory access, memory would be done in a couple hundred cycles, and you'd still be spending 100,000 cycles to be swapping your thread out. It makes no sense. So they're the same idea, but at very different orders of magnitude. Okay, so the rest of the time I actually want to go through a case study or two with you of the first time we're actually going to really start kind of optimizing programs. I mean, you have to, I guess, optimize programs a little bit in assignment 1, but it's not super crazy. And, you know, our goal is going to just be get the maximum speed up for now. Our goal is to, like, reduce the timer by some factor. And hopefully, you know, if I can do things, if my time is p times less, then I have this, you know, p speed up. And I think it's somewhat helpful. You know, every year I decide whether or not I should show this slide. I think it's useful just to talk in general abstract terms for a second about kind of the process of parallelizing a program. And the process you can think of as, like, you know, what is step 1? Step 1 is almost always figure out what is independent. Divide work, you know, figure out what are the things that I could do in parallel if I want to. And you know, terminology is kind of weird, but decomposition is kind of something that I think I use to say that. It's like, I got a problem, I need to decompose it into things to do. Sometimes people might say tasks or something like that. And then there's the problem of assigning those tasks, assigning that work, really what I should say, to things that can execute the work. And so you'll often hear me say assignment to mean that. So decomposition is going, oh, we can work in parallel. And assignment is like, okay, I'll do this and you do that. Right? And then, of course, at some point there's often you know, some orchestration or some synchronization because we have to sync up. You know, we might have to compute a total sum, or it might need to be like, when you're done, I'll go. You'll see me call that orchestration. And last, like, there's often a notion of mapping, of like how does, like, some worker actually get to the hardware. So I'll give you some examples of that in a second. So in this class, you are almost always going to be the entity responsible for decomposing a problem into smaller pieces that can be done in parallel. The magic compiler that does it for you largely does not exist unless you're using very specialized computing languages. Okay? And it's a little bit shocking to see how your speed up is limited if only a pretty small fraction of your program is not parallelized. So let's say we had a program that had some runtime, and imagine that the fraction s of that program was serial. So let's say you have a program and have half the program just is inherently serial, or maybe you just don't get around to parallelizing it, s is 1/2 here. Okay? If 10% of the program is serial, s is 0.1. So then the maximum speed up you could ever hope to achieve if you perfectly parallelized the other part with an infinite number of processors is sort of 1/s. Because your runtime is at least s. And so, you know, if your total time over you're limited by 1/s of your speed up. And this can actually be pretty dramatic. Let's look at this. So here's a simple example from programs that I kind of write all the time, which is, imagine I had an image of me, and the goal was to multiply all pixels by 2 to increase the brightness. And then maybe I wanted to compute the average of all pixels. It's actually a pretty common operation that your camera does all the time. Both steps, hopefully you can see, take n squared time. They're n squared pixels. It's an n by n image. And if I plotted things out, like, this is execution time, and this is the amount of parallelism when running. So if this is a sequential program, right now the implementation has parallelism 1, and it has time 2n squared, right? 2n squared. So what would be the first step? What do you identify couldn't be done in parallel?
All at the same time.
I can definitely compute the brightness of every pixel independently and potentially in parallel. And let's say that we run this on a machine with P processors. Now, I'm going to use the term P processors because you could think about it as a processor with P cores, or we can think about it as just like distributed computing with P processors. The details of that don't matter. But let's just say we had P things that could run in parallel. Well, if I take your strategy, then what happens is the front part of this program now goes to time n squared over P, and I haven't touched the back half of the program. What's my speed up? Perfectly parallelized the first part of the program, didn't touch the back half, but my speed up is what? In the limit, let's say as n is huge. Sorry? It's twice, right? So what is my overall performance? Well, it used to be 2n squared, and now it's n squared over P plus n squared. And in the limit, that's going to go to bounded by 2. Right? So half my program remains sequential. There's nothing I can do. I can't be any fancier here. If I went to 1,000,000 processors, I would still be bounded by 2. Okay. Now, what else could we do? Yeah.
If the average, use the partial sum to get the sum of all pixels.
Yeah, so I can take all my processors. Every processor could take like one pth of the image, compute a sum, and then I got to do what at the end? Well, yeah, you're speaking about it in terms of like if we had to write an Ispc, but conceptually, every processor does one pth of the sum, and then if we just naively add p things up to get the final answer, that would be plus p here at the end, right? So I have n squared, n over p. So I have 2n over p squared plus p if I added the partials up sequentially. Did everybody see that? So the real question here is like, if p is very, very small compared to n, I'm going to be doing great. If p is actually kind of substantial compared to n, then I fundamentally still have some problems, right? And so this factor s is actually pretty important. So here is a plot where this is the total number of cores, number of processors, 64 processors. And this is a theoretical optimum speed up for programs that have different s's. Right? So let's say that only 1% of your program was sequential. And you run that thing, and the other 99% is perfectly parallelizable on a 64-core box. You are limited to about 40x speed up. That 1% of sequential really starts to bite you. And so I'm already like not perfect scaling on a machine with 64 cores. If 10% of my program can't be parallelized, my best case scenario on a 64-core box is about 8x. It's pretty dramatic. Now imagine you're not running on a 64-core machine, but you're running on a big supercomputer that has approximately 150 million parallel units. You better get that sequential portion of your code down to like 0.0000001% of the problem. Otherwise, you might as well not be using this thing. Luckily, most of the code we run is going to be pretty parallelizable. So, like I said, like in this class, understanding how to decompose something is going to be almost just like what we did here. It's going to be up to you to give write a program that decomposes things well. Don't hope for magic there. But what we often might rely on systems for, programming languages or compilers, is to assign that work to workers for us. Okay, so assignment might be something like, the name of the game in an assignment is to keep all of my workers busy. So you might be responsible for assignment. For example, earlier in this lecture, I wrote 2 different Ispc programs where in this program, I assigned loop iterations to program instances. I wrote this code, so I decided that this program instance was going to do this iteration. I assigned it. I gave you a different version of the code where I said, Ispc, I'll let you do the assignment. I trust you to do as well or better than me. So that's an assignment task right there. On the first day of class, I think I showed you this piece of code where I had a C program that spawned an additional thread, and in this code, I assigned one half of the array to one of those threads by the nature of the code that I wrote, and I assigned the other half of the array to another thread. Right? So I assigned who does what. In Ispc tasks, you are decomposing this problem into tasks, but you're telling Ispc, I will let you assign these tasks to the running threads that you have to do the work. So under the hood, there might be a pool of threads, like one that you implemented in 111. And Ispc is going, is there an idle thread? If so, hey, could you please work on task 0? Or are you idle? Could you please work on task 1? Oh, you just got done with the task? Well, the next available one is task 42. Could you go do that? That's what's going on under the hood. And most of the time, we would rather have the computer, the system, do the assignment for us because we're going to assume that they're going to do a better job than maybe we would. Or maybe there are different assignment strategies that are the right assignment strategy for different computers. And I don't want to have to write my program with a specific computer in mind unless I really, really care about performance. We won't talk too much today about orchestration, but you saw one example of it, like that reduce add or those cross-lane calls. But at some point, even if you are divvying stuff up into to different pieces, those workers are going to have to communicate and synchronize. You know, one example of synchronization would be these workers have to synchronize so that every task only goes to one worker, and every worker goes to the gets the next task. So there's going to be a little bit of synchronization, and you saw the effect of that synchronization in my demo that I just showed you, in that my thread pool was still slower than the sequential version of the algorithm because my threads were synchronizing to take the next task. So that was an example of synchronization. And then last, like at some point, someone has to actually take this idea of a thread or a program instance and map it to an actual piece of hardware. That's the last step of this. So, we talked about orchestration and then mapping it to hardware. So, for example, imagine you create a thread. Who maps your C++ thread to a hardware execution context? We just talked about it. Operating system. In Ispc, who maps a program instance to a vector lane? That's like kind of like built in the implementation of the compiler. Exactly. And there's a bunch of interesting mapping decisions. Like imagine you're the operating system, and imagine your program creates 2 threads, and you're running on a myth machine. If your program creates 2 threads, and I'm the operating system, do I put them both on execution context on the same core, or do I put them on different cores? It's a policy decision that one could make, and there are different pros and cons. Okay, so let's dig in with a little bit stronger case study here. How many people, do we have any SMNE, not SCPD, like any numerical computing folks? Any scientific computing folks in the, almost always are. Okay, no. How many people have implemented a solver, an iterative solver in a numerical methods class? We got some folks. Cool. What solver did you implement? Yeah, you did a Newton's method solver. Okay, so here's not similar idea, but here's like a grid of stuff. So imagine we had like this is actually from a fluid solver, where we have a grid of values, and at every value there's like a pressure or some quantity, and the goal is to bring this system to convergence. And the details of that are not that important, but computationally, what it basically is blurring out the grid. The new value at location yellow is going to be the average of the surrounding values. Okay? So we're trying to we're going to iterate on this and just kind of bring this to convergence, so that like if I change the blue value here, that should cause some update in the yellow value. Now look carefully at my code here. This is the starting code we have. While not converged, for every element in the array, now by the way, this is just pseudocode, C like pseudocode. For every element in the grid, save off the previous value, and the new value is the combination of my neighbors, and then I'm accumulating the total amount of change of all values. And if the total amount of change over the whole grid has changed enough, we'll stop, or we'll keep going. If nothing is changing anymore, we've converged and we've stopped. So step one of anything, whenever I slam code up here, is I'm going to ask you, what can be done in parallel? So take a look at this, and if we respect the code as is, what is the challenge that makes us go, uh-oh? Yeah.
Doing A of ij on all the neighbors, which we also have to compute, so the code is not
aij depends on my neighbors, but my neighbors just got updated in the previous iteration of the J loop. So I cannot do the next iteration of the innermost loop until I complete the previous iteration of the innermost loop. So your dependencies might look a little bit like this. The red arrows say that the black dot is dependent on another dot if there's a red arrow from an external thing to me. Okay? So if I asked you to parallelize this code, and this was the code, is there anything you could do?
Different chunks that are touching each other.
Well, okay, but so let's say I did the top left chunk completely sequentially. What could I do in parallel with it? But I can't do the top right chunk because none of these values are known until all that information propagates. So, yeah, so I can't quite do that. I might get the wrong answer. Yep. Sorry? But if I make a separate result array every loop, I'm going to compute a different answer. Because my value at this iteration depends on previous computations in the same loop. So if I write the new result to like A2, something else, I am not computing the same thing. Any other thoughts? Yeah.
You could sweep diagonally.
So there is a little bit of parallelism here. There's a little bit of parallelism here. So you could be really clever, and you could say, well, at certain parts of the program, there's at least like sort of like a little bit more than O of n parallelism. But I'm kind of like, I don't even know if I want to write that code. I don't know if I want to write that code for two reasons. One is I don't have a lot of parallelism in large parts of the program. So Amdahl's law is going to get me. And second of all, if I'm actually moving in this direction, I'm all over the memory address space. And so it's not clear that it's necessarily going to be a benefit to me anyways, even if I got some parallelism. So here's what we're going to do, which is a big part of often thinking about programs. And when we do a mini transformer in assignment 4 this year, this is going to be a big part of it, is sometimes you look at a program and go, I don't really want to bother with this. This is not a program that I'm going to have a lot of success with. So what we're going to do is we're going to look at it and we're going to use our knowledge of solvers and go, there's another solver that will compute approximately the same answer but is more friendly for parallelism. Okay? So that's what I'm going to do. We needed some domain knowledge. You got to go talk to your expert, or you got to be an expert in machine learning, or you got to be an expert in graphics or something like that. We're going to change the algorithm a little bit to a different algorithm that's way easier. And that's as we're going to do this checkerboarding thing. And we're going to iterate back and forth, which is on one step, I'm going to take all of the red cells and update them based on the black cells. And then on the next step, I'm going to flip it around and update all the black cells based on the red cells. So I hope you can convince yourself that I can do all of the red cells in parallel. And then I can do all the black cells in parallel. Okay? Now I've changed the algorithm, which by the way, I told you just a second ago you can't do that. But now this is like, we had nothing to do. So it's like, okay, let's go to a different algorithm. It's more friendly to parallelism. It turns out that this new algorithm will actually take a little bit longer to converge. We're actually probably going to need to do more iterations. But the cost of doing some extra work we're hoping can be made up by the ability to massively parallelize if we have a big parallel computer. Yep.
What
question about both the algorithms. So they will converge to the same value, right?
I'm just asserting that, and I want you to trust me for now, right? Like, or they're going to converge not to the same numerical value, but this is already an algorithm that's like good enough, right? So as long as it converges to some threshold, we are scientifically happy. Yes.
With domain-specific accelerators, why wouldn't you right now think about using hardware to solve this? Probably something like a systolic system might be able to help with the first approach.
Yeah, so you are correct. One possible solution would be, let's go build some custom hardware for this. Now, the hardware does have some scalability issues in that there is only so much parallelism here. But you're also proposing a pretty expensive solution to the problem of go designing a $100 million accelerator to handle this thing that you have 2 weeks to do the assignment. Okay, so that was decomposition. So we've decomposed the problem into let's do all the red stuff in parallel. So every red dot is something independent. And now we need to kind of think about assignment. Let's say if I'm going to chunk this grid up into 2 possible assignments. Let's say I'm going to divide them in a blocked way across the processors, or I could divide them in an interleaved way across the processors. 2 valid ways to parallelize this program. Who knows what might be better? There could be some issues that lead us to do one over the other. Okay? But that would be an assignment decision. So let's consider the dependencies in this program, right? We're going to compute all of the red cells, which means every red cell needs to access its neighbors. And then I'm going to send all processors. Everybody needs to be able to get the updated value of the red cells so that we can then do the black cell update, right? So when I think about it, like this program that I've written occurs in phases. So in this particular case, if we decide to put contiguous blocks of this array local to various processors, there's much less data that needs to be exchanged. Because if I'm, let's say, processor 4, I just updated these black cells, or these red cells, well, I already have the information I need to update my black cells. Whereas if I would have gone with some interleaved mapping, every single thing that I compute has to get transferred to my neighbors at some future time. So there can be some issues related to what, given the knowledge of the program, in this case, I'd probably do this kind of blocked assignment as opposed to interleaved. But when we were talking earlier about Ispc programming on SIMD hardware, we actually made a different conclusion. So you need to know what you're running on in order to think about the thing. Okay, so I want to write this solver now in 2 different ways. The first way, we are not going to think about threads or parallelism at all. We're just going to think about parallel work. It's very much like the foreach way of thinking about things. And then I'm going to come back and rewrite it in a way that's more like, here are all my workers, and here's how they communicate to solve the problem. So I'd very much rather, as a programmer, write it in this more, I'm going to just think about parallel work. Okay? So here's a version of that. Now I'm stepping out of Ispc just to be in pseudocode. This is just pseudocode. We're not thinking about SIMD. We're just thinking abstractly right now. Uh-oh, that might end up down here. Okay, so I kept this simple, and this is only code for just the update of the red cells. So there's another thing down here, but just the updater. So for basically, look what this says is there's no parallelism at all. I just have a program that runs sequentially, logically, but here instead of a regular for loop, I just wrote it as a for all red cells independently, please do your red cell update, and then using some helper function, which we magically have available to us, please go ahead and compute the amount of update that this iteration did. Please accumulate it into this global variable diff. Does that make sense? And we've left everything to the system to figure out how to parallelize. We've said, trust me, these iterations are almost completely independent. The only thing you have to worry about is that I want all the information that I'm computing to get correctly added into this global variable. So I am kind of thinking about parallelism a little bit here because otherwise I wouldn't have written this. But more or less, I'm leaving I've done the decomposition, and I've said assignment, parallel system, you go figure out for me. Make sense? Okay. And this is why I'd rather write it this way, because it's basically the sequential code. I just did one little thing which said, hey, compiler, trust me, all these iterations you can do in parallel, provided that you take a little bit of care right here. Now let's step down to a lower level and see how we might write it ourselves with lower level abstractions, or another way to think about this is, if you were the compiler at runtime, how would you implement this? Which at the end of the day, someone needs to decide who does what. Okay. So now I want you to think about kind of Ispc programming or threaded programming, whatever programming model you want. We're just going to have a bunch of threads running in a shared address space. Okay, so everybody can access shared variables. We have one address space. But we're going to have to synchronize with some constructs like locks and barriers. So here's my implementation of this code. Now, it's a little bit long, so I've tried to sort of explain it to you. I've tried to sort of annotate it here. But it's doing the same thing. It's saying, while not converged, this is code that's run by every thread in the system. So if this was Ispc, this is like the code running by a program instance. If this was threaded C programming, it's just the thread. And in the same way that I could get my program index, in any threaded system, you have the ability to get your current thread ID. Right? So you have some way of knowing, out of all the running things in the system, which one am I? Because I need to take that information about which index I am and turn that into some decision about what work I'm responsible for doing. Okay? So given this thread ID, notice what happens here. I want you to ignore all this jumbo about locks and barriers and just look at this. It says, I'm going to compute the rows that I'm responsible for, my min and my max, which is a blocked set of rows. And for all elements between row my min and my max, I'm going to do the update. And I have this local variable, my diff, which I'm accumulating my local stuff into. Okay? And then at some point, I take my diff and I add it into a global variable diff for all the threads. Okay? So this is like just you could write this in C++ if you wanted with C code. Okay? All right. So my question to you is, what is this lock doing here? Why do I have lock, unlock around this line of code? Yeah. Okay, and what could go badly if I did not lock that? What's that?
Race condition.
It's a race condition, but yeah, I mean, true. But what could go, like in the specific terms of this program, what could go badly?
Some thread could read diff while some other thread writes.
Okay, so we need to make sure that this change to this shared variable is atomic. Okay, let me elaborate on that a little bit. So let's go think about a simpler example. Imagine I have thread 1, which at some point writes 1 to some variable x. And I have another thread 2, which also has access to variable x. And whenever it's non-zero, we're gonna print x. You know, we'd really expect x to be printed to be 1 here, right? So you can kind of think about this shared address space as this is what you've thought of any computer. There is some memory address space. There's an address x, and there's a value at x. And all my threads have the ability to read and write to that value. That's just the notion of computer that I haven't even taught you, but you naturally would have assumed. People like to think about a shared address space as like a bulletin board. You can go to somebody's door. Anybody can read and write. Could be some problems if we read and write to the same spot. Okay. So the reason why we protect updates to shared variables with locks is, let's think about what can happen when we think about what does it mean to write to a value in memory. When I have like an x++ in my code, what that really means is load the value in memory into register R1, then perform the math on R1, and then store that value back out to memory. There's actually three operations here, even though it's one line of code. So imagine that the value in memory was 0 as we started. T1 would load 0, update it to be 1, and then try and store 1. What if at the same time thread 2 went in there, tried to do x++? It also read 0 because it read the value before T1 had written it. It updates it by making the value 1, and then later writes 1 back to memory. We would miss an update. So this is a race condition because we don't have mutual exclusion. We don't have a policy set forth so that only one thread is writing to a shared value at once. Okay? And what the lock does is the lock provides that mutual exclusion. Only one thread can have the lock at once, which means only one thread could be writing. Later in the course, I'll tell you about other really helpful primitives that allow you to ensure mutual exclusion without locks. But in this example here, that's what that lock is doing. And that's something you would have seen probably in 111 with your thread pool, just a review here. Now, in the context of this program, what could happen if we didn't have the lock? What would be the effect on the program? The total diff value would be what? Lower. Potentially lower than it should be. And some threads might falsely conclude that they should terminate. Right? So that would be the effect here. The incorrect assumption that things had falsely. Now, this code is correct. But now there's a performance problem here. Something I really don't like. Oh, sorry. Actually, I already fixed it. Shoot. I meant to do it. I've already actually fixed it in this code. So the original code had this lock and unlock update here. And in a copy-paste thing last night, I actually copied the better version into here. So my original version was don't even have a mydiff. Just do a lock and update global diff. Right? And the problem with that is I'm doing this synchronization in my innermost loop. Right? So my solution here was to actually create a private copy of my diff, have everybody update their partial diffs without locks, and then come back together at the very end of the iteration and compute the overall sum before we actually did the check. Sorry about that. I was looking about that. I was like, there is no performance problem with the code. Okay. But now the last question I want to ask you as we finish up is what are these barriers doing here? You might even be asking me, what is a barrier? Right? So what a barrier is, it's another form of synchronization. If a lock is about mutual exclusion, only one thread can hold the lock. A barrier is a very coarse frame of synchronization where you can phase your computation. So a barrier says no thread, the caller will not proceed past a barrier until all threads have gotten to this point. Okay, so say, once I know everybody is here, then we can all continue. Okay. So my question is, why do I have 3 barriers in this code? I kind of intuitively would think I should probably have 1. I should do all my work. We should wait for everybody to get done and accumulate into my diff. And then we just should do a check and we should keep going. But this code is correct. And I have 3 barriers in it. And if we have 4 minutes, the last thing I'll ask you to do today is why don't you see if you can talk this over. What is the purpose of all 3 of these? I claim I need them. So, wake up for 1 second. Okay. So since we have 2 minutes, let's see if we can talk it over. So I think the first one to really look at is to be the one that's the most obvious, the second barrier here. Why did I put a barrier in the code? Here. Yes, sir.
For all threads in order to get the correct diff value for that iteration.
Before any thread checks to see if the system is converged, we need to make sure that all threads have performed this update so that we're looking at a correct diff value. That makes sense. Okay. So let's say we decide to that done is or we want to continue. What happens if this barrier is not here and I immediately shoot up? Yeah.
One thread could just go and set the diff to 0.
So thread 0 might be like, okay, sure, we got to keep going. All right, let me get started for the next iteration, setting global diff to 0, and then what happens? All other threads might be like, shoot, by the time I got around to checking it, it's 0, we should stop. Good. Okay, so that's why I need this one, because I don't want people to clear that value before I take a look at it. And then what about this one? The last one?
Oh, a thread might update the diff in the block, and that might change the value.
So what if in the next iteration I get all the way through my work and I update the diff value before in the previous iteration the other threads have actually been able to check it? And if that allowed to happen, then the diff value would be incorrectly too, well, who knows what it would be. I've set it to 0 and then I've updated something into it, so it could be too large or too small. It's just wrong. So you see how I need all of these here to have this correct program. So my challenge to you to end the lecture is, it is possible to do it with 1. Can you do it correctly with 1? And the hint would be, take some inspiration for what we did here with the diff variable. Is if we didn't have a local mydiff and we had one global diff, every single time I wanted to access diff, I would have to lock it. But what we did is we had contention, so I made local copies of something in order to remove the contention by replicating some stuff. Here, what are we contending for with the barriers? What's the variable that we're all making decisions off of? Diff. And the problem is that we're reusing the same diff variable across different iterations. Is there any way you can replicate something in order to remove this dependency? And you can get it down all the way to 1, and this is the only one you actually need. So I'll stop there, and that's just a fun one to talk about on the website.